Hello students, so welcome to this lecture. This is the second part of the stick diagram representation, and in this particular lecture we will talk more about a particular way of designing or ordering the poly gates so that we can complete the stick diagram very efficiently. Okay, so this is what we had seen in the last lecture. So we had a combinational circuit of AB plus CD and then the inverted form of that or the complement form of that. The schematic is given on the left hand side where we have the inputs A, B, C, D connected to the pull up circuit and then the pull down circuit. And we have the PMOS transistors and then the NMOS transistors completing this particular combinational circuit. So what we had seen in the last class was the ordering of the polysilicon gates where the order should be A, B, D, C and not A, B, C, D. So it has to be in an order of A, B, D, C so that we can use the merge diffusion and then contacted merge diffusions or uncontacted merge diffusions. And remember that if you have the merge diffusions, then the overall layout or the overall stick diagram can be very, very compactly designed. Okay. So what we will do in this particular lecture is try to follow a particular method called as Eulers path. The Eulers path will help us in designing the polysilicon gates A, B, D, C, or rather I will say that it will help in ordering our polysilicon gates. So for this particular circuit, if we were to design the polysilicon gates in the layout, instead of A, B, C, D, it will be the order will be A, B, D, C, and that has been arrived or that has been deduced from the Euler's path, right? Although we have not seen the Euler's path, we just took one such example. Instead of A, B, C, D, if we use A, B, D, C, then we can get a compact one. So we will see how to use the Euler's path for designing the stick diagrams, right? And then identify what should be, or then estimate what should be the overall footprint. So the Euler's path, especially for this particular circuit, so let's try to define this. So I have actually put two Euler's path, one for the pull-up circuit and then one for the pull-down circuit. The Euler's path recognizes all the nodes in the circuit design. So in this particular pull-up part, we can say that VDD is one node, the X is another node, and then of course the Y is another node. So there are three nodes in the pull-up side. And then in the pull down side, we have, the Y output node is one node, and then there is one, the merge diffusion, which is uncontacted one. And then there's a ground one. This one and this ground are same. So I will have Y output node and then this one node and then the ground node, and then we will have one more node. So the Euler's path for the pull-up and pull-down circuit should consist of all the nodes that are available in the schematic, so that we need to represent that in the Euler's path. So in the pull-up side, I have written the nodes of VDD, I have written the X node, and then I have written the Y node. And in this particular path, if we are trying to visit from one node to the another node, we will also try to label or annotate the polysilicon gates, or rather the input to this particular PMOS transistor, which is nothing but the polysilicon gates. So while I am traversing from one node to another node, let me also write or label the polysilicon gates here, which is A, B, and C and D. Right. So in this particular Euler's path on the pull-up side, we will see that it forms a shape. So if I am starting from VDD to X node, so I will have I will traverse the B node, right? And then from X to Y, I will travel either the C or the D node, and then I'll traverse back to the X node with the left out node, whether if it was the C node which I have traversed earlier, then I will use the D node path, and then it will traverse back to the VDD through the remaining polysilicon gate, right? So just to reiterate, so I will travel from node VDD to X node, traversing the P polysilicon gate, and then from X node to Y node, I will traverse using the C polysilicon gate, and then from Y to X node using the D gate, and then from there to the VDD traversing the A polysilicon gate. So that is one particular path, right? But this particular path, it is actually says that it is revisiting the node and traversing the polysilicon gate only once, right? I can also have multiple combinations. I can have one combination starting from, whatever I have written here, starting from the polysilicon gate A, right? So that means that it starts from the X node, passes the polysilicon gate A, and then goes to the VDD node, and then comes back to the X node through the B polysilicon gate, and then goes to the Y node through the D polysilicon gate, and then from Y to X back, traversing through the C polysilicon gate, right? So the nodes could be multiple, there could be multiple visits to the nodes, but the polysilicon gates here should be visited only once. Okay, so the nodes could be visited multiple times, but the polysilicon gates has to be visited only once. And similarly, on the pull down side, we will have one particular path, starting from Y to A to B, and then to ground, and then traversing back to D and C, back to Y, right? So here also I have the polysilicon gates A, B, D, C. And here also I have the polysilicon gates traversing in the order of A, B, D, C. So if I define the paths, the Euler paths, where the polysilicon gates are visited only once, right, for both pull up and pull down side, and if the order on the pull up and pull down side matches, if the order of the polysilicon gates on the pull up and pull down side matches, then we are bound to get a compact footprint. Right, so that's what I've written here. Euler's path is a path that is followed through the different nodes and multiple visits through the nodes, but where the transistors are visited only once. And the sequence of visiting the transistors in the Euler's path for both pull down and pull up, if it remains the same, then we can arrange the polysilicon gate in the order as suggested by the Euler's path. Right, so in this particular case, in this particular schematic, what we have seen is the pull up and pull down circuit. We have got the same order of polysilicon gates, that is ABDC on the pull up side and ABDC on the pull down side, and then this order, if it matches, then we can get a compact circuit. Right, so moving ahead. So this is now the stick diagram, and this is something we had already seen. So I have a VDD rail, I have a ground rail, I have a P diffusion, I have an N diffusion, and I have the polysilicon gates ABDC. ABDC, that is the order which is suggested by the Euler's path, and this gives us the compact design, and then the width of this and then the length of this is stated here. So let's now have a look at the width, overall width of this particular stick diagram. So for estimating the width of this particular stick diagram, we need to number the metal tracks. So the number of horizontal metal tracks will be 1, 2, second is for the P diffusion line. And then we have the third line here, and then the fourth line here, and then the fifth line, which is nothing but connects to the output node. The sixth one is the N diffusion line, and then the seventh one is the ground rail. Right, so I have 7 rails, 7 metal rails multiplied by 8 lambda. But if you look at the sizes of this gates of these transistors, if I go back, if I notice the sizes, it is actually different than that of the scaling of 1. So if I have the size of 4 and 4 here on the PMOS side and 2 and 2 on the NMOS side, so my P diffusion line is not anymore 4 lambda, it has to be 12 lambda. Right, and on the N diffusion side, the N diffusion line is not anymore 4 lambda, it is now 8 lambda. So moving ahead, so I now have 4 lambda multiplied by 3, so that is 12 lambda has to be accommodated in this particular footprint for the P diffusion line. And on the N diffusion side, I have to accommodate additional 4 lambda multiplied by 1. The overall length of this particular footprint, if I want to track the number of metal lines, it is nothing but this particular metal line is 1. The second one is this one. The third one is this one. Fourth one is this particular line, and then the fifth one is this particular line, which is aligned here. So I have 5 metal tracks, vertically, and then multiplied by 8 lambda will give me 40 lambda. Multiplication of this width and length should be able to give me the overall footprint In terms of lambda square, of course, we can always identify what should be the absolute the footprint by considering lambda with regards to the technology node. Right, so moving ahead, this is one more example where we have the combinational circuit of AB plus CD plus EF and then the complement of that. So last time we had seen AB plus CD and then the complement of that. Here I think there's two additional the inputs E and F. So this is the circuit, the schematic diagram in the transistor level. So I have AB in series, and then that is in parallel with that of the CD transistors, which will be in parallel with that of the EF transistors, which are in series. And because it's a conduction complement, I will have the AB on the pull-up side. I will have A and B in parallel with that of in series with that of CD, and then in series with that of EF transistors. Right? I'm not written down the sizes of these transistors, that we will have a look at it later. And if I want to use the Eulers path, so I will identify all the nodes in the pull-up side and then in the pull-down side, and then try to traverse through the nodes, visiting the polysilicon gate only once. I will try to do that. So I have identified the nodes VDD, I have identified X1 node, I have identified X2 node, and then I'm trying to form a path. So here the path is again, you can have an A VDD, B X1, and then D X2, and then C X1, right? And I cannot have X2 going to Y without traversing the polysilicon gate only once, and that's why I have separated it out now. So now I have actually separated it out, the X2 and then Y, where it is traversing from X2 to Y. And then Y to X2 through the polysilicon gates E and F, right? So I cannot have actually A, B, and then D, and then go to E, F, and then cover back C. So that that will be difficult. So in that sense, what we have done is we have separated it out, and then on the pull down side we will have again because on the pull up side we have A, B, C, D. As one particular path, and then EF as another path. We will also cover the paths of A, B, C, D on the pull down side in one path, and then E and F on the another path, right? So on the pull down side, we now have Y connected to the ground via the A and B polysilicon gates, and then coming back to Y via the D and C polysilicon gates, right? And so that will be for this particular path. And then we will have for this particular path, we will have the X2 go to the Y via the E and F polysilicon gates. And then on the pull down side, we will have the Y connected to the ground via the E and F polysilicon gates. So the gate sequence, which is actually matching with the two Eulers path now for the pull up and pull down side. So if I consider this particular path, so I will now have a gate sequence of A, B, D, C, right, which is matching for both pull up and pull down side, and here it is matching with that of E and F. So I will now draw the stick diagrams where the order of the polysilicon gates is A, B, D, C, and then E and F. So A, B, D, C part will remain the same. It is very similar to what we had seen in the previous case. E and F, it's very interesting. So I have now the nodes X1 and also I have the node X2 here. So X1 is here, and then I have written the X2 node here, right? So, and then I have to draw the E and F polysilicon gates. Notice that there is a separation here, right? The separation indicates that the transistor E and F has one merged diffusion, that is this X2 node. Right, and on the other side, it has a merged diffusion node, which is a Y output node. So this is the Y1 for the F transistor, and then somewhere there is a, and then this is a Y node for the E transistor. On the other side, it is the X2 node. Right, now this Y and then this X1, this Y and X1 are not connected, and therefore I should not have this diffusions to be connected. Right, so I cannot have the merge diffusion here. That means that there should be a separate diffusion, and if there is a separate diffusion, this distance between the diffusions should be a minimum of 4 lambda, right? So it should have a 4 lambda separation. On the pull down side, I have the AB DC and then I have the E and F polysilicon gates. So AB DC, it is very similar to the previous case. And then so the Y output node will come to the X diffusion here, and then A and B will have a merge diffusion, and then you have the D and B, the merge diffusion gets connected to the ground. That's what I have here. And D and C will have the uncontacted merge diffusion, and after C, that is the after C is the output Y, so that gets connected here, which becomes the merged contacted diffusion between the C and E transistor, C and E transistor. So I will have the merged contacted diffusion which goes to the output node Y, and then E and F will have this particular portion is an uncontacted merge diffusion, and finally the F transistor, the diffusion of the F transistor will get connected to the ground. Right. So notice that there is a separation of 4 lambda that is very much required. Otherwise, the X1 and Y point will be the same. So if I now want to find out what is the number of horizontal tracks and then the number of the vertical tracks, here I will have the vertical tracks as 1, 2, 3, and 4, 5, 6, 7, 8, and the horizontal tracks including the P diffusion and N diffusion lines will be 1, 2, 3, 4, 5, 6, and 7. So the overall length will be 8 into 8 lambda, and then the width will be 7 into 8 lambda. And of course, 4 lambda separation within the diffusion is accommodated in the extra metal in the length. So what I meant was the 5th and the 6th line anyways has a separation of 4 lambda, which is anyways taken care for the separation of the diffusion. So I need not have to accommodate this extra 4 lambda. But mentioning that there is not a straight line is very important, because then if it's connected, although there is a separation of 4 lambda between the metal lines, what it indicates is the diffusions are connected, right? So you have to ensure that in the stick diagram as well as in the layout there is a separation, right? Those lines, the P diffusion lines, are not there. The last one. So here is a stick diagram, just a 3-input NAND gate stick diagram. So the schematic is given here, and then I have drawn this the stick diagram here. The stick diagram is very, very simple here. The VDD line, and then the ground line, and then the P diffusion, and then the N diffusion line. So let me try to complete this particular stick diagram. So if I consider the A transistor, B and C transistor, so A, B, C, and then in this order, so the Eulers path will go to A to VDD to B to output to C to VDD. So I will have on the pull up side, I will have the order of polysilicon as A, B, C, and then on the pull down side, the Eulers path will give me the order of A, B, C, right? So Y to ground, I will get an order of A, B, C. So in that sense, I will have the orders matching, and then I can have a very compact stick diagram or the footprint design. So that's what I've drawn here, the polysilicon gates ABC. On one side of the polysilicon gate, it is connected to the VDD, and both B transistor and A transistors are connected to the VDD. So that means that the A polysilicon and B polysilicon, the merge diffusion, I've connected it to the VDD. On the other side of A, it is connected to the Y output node, and B is also connected to the Y output node. So on the other side, it is connected to the Y output node, and on the other side of the B, which is this B and C, we can consider it to be a merged contacted diffusion, and then it gets connected to the Y output node. The other side of the V will go to the VDD, so the other side of V diffusion will go to the VDD. So this completes the connections of the diffusions on the pull-up side. On the pull-down side, I have the A, B, and C, so the merged uncontacted diffusion, here. So A and B, wherever it meets, it is this particular point, which is U point, and B and C, wherever it meets, or the merged diffusion is there, that is the V point. The diffusion, the last diffusion on the C transistor is anyways connected to the ground, so that is implied here. And the first diffusion of the A transistor is connected to the output node, so the first diffusion of the A transistor is connected to the Y output. All right. This particular stick diagram, I have drawn this not to estimate the overall footprint, but just to estimate what should be the overall capacitance. right? So in terms of schematic, if I want to estimate the delay, I will actually draw the capacitance, the parasitic capacitance, the internode diffusion capacitance, and then try to evaluate the delay in terms of RNC values. Here, what I've done is I've taken the capacitance 2 from the A transistors on the PMOS side, another 2C capacitance from the B transistor, and another 2C capacitance from the C transistor. And then the 3C capacitance from this side, indicating a total of 9C capacitance. And this is what we have been doing. The internode merge diffusion capacitance on the NMOS side, we had taken or considered 3C and then 3C here. Right? But if I really look into the stick diagram, right, especially on the pull-up side, there is a slight difference. Right? So if I consider the U point here on the pull down side, I'll see a merge diffusion, and if the width is 3, I will get a capacitance of 3C. And V point also, if it's a merge diffusion, I'll get a capacitance of 3C. On the pull-up side, this B and C transistors are actually having a merge diffusion capacitance and a contacted merge diffusion capacitance. So the diffusion is actually single. So this particular point is going to give me a capacitance of 3C, or rather, a capacitance of 2C, because the width here is 2. So that means I will have 8 lambda scaling. So whatever is that, it is the scaling of 2 implies that it is 200 nanometers, not 100 nanometers. 100 nanometers will give me a capacitance of 1C. 200 nanometers will give me a capacitance of 2C for one diffusion. And since B and C are actually merged, I will get only one 2C capacitance. A will give me one 2C capacitance. So the total capacitance coming from the PMOS side is actually 2C and then 2C. And then on the NMOS side, it is actually 3C. So the total capacitance turns out to be 7C here, rather than what we have been using is the 9C capacitance. Right? And this is actually very, very useful in that sense that the overall capacitance has come down. And in fact, it actually comes down in a stick diagram or in the layout design. And overall performance or the delay is actually less than that what we have been calculating using the linear delay model or in the Elmore delay model. Because in the Elmore and linear delay model up till now, we have not been considering the merge diffusion capacitance coming from the pull-up circuit side. Right? We have been always using a very linear combination of this particular the capacitance associated with this transistor, capacitance associated with this transistor, capacitance associated with this transistor whenever the transistors were in parallel. We used only the merge diffusion capacitance whenever the transistors were in a series. But in fact, from the stick diagram, we can easily see that if we make it very, very compact design, make use of a lot of merge diffusion capacitance, the overall capacitance seen at the output node also decreases. Right? So instead of 9C, it is actually 7C. And 7C will naturally have a much better performance than that of the 9C capacitance.